Is we want to take you through everything it takes to move your robot from this one on the left, sorry RC, that kind of drives around and maybe doesn't score so well and stuff falls over the place and not exactly what you want, into something on the right, which can track the goal pretty well and move around quickly and accomplish your strategy task. So what we're going to go over in this presentation is kind of a overview of what we've done with vision and FRC over maybe the past 10 years. And then we'll talk about why you'd want to use this on your robot. We'll do a little section on, I want to use vision, I've determined I want to use vision, let's get my robot to point at a target. How do I do that? What hardware do I need? What software do I need? How do I control my robot to do that? What's the simplest way? And then working up through more and more complex solutions until you have something that works really, really reliably. And then after that, we'll do a couple of more advanced techniques, like if you want to figure out how far away you are from the target. That's something that people often have trouble with. And then we'll go over some more just high-level best practices. And of course, plenty of time for questions. So why is this important? Over the past couple of years, the FIRST robotics competition has become more and more technically challenging. Every year the goals get smaller, the robots get faster, and every year, all of you who are in this room listening to a presentation are building better and better robots. The bar just keeps getting higher and higher. So every year, if you want to compete at a high level, you need to build a better robot. And part of this is software. We finally got to the point where you can go and buy gearboxes, arms, any kind of actuator off the internet from Vex or AndyMark or something. And what's setting teams apart now is their ability to successfully execute software tasks. And there's a lot of cheap hardware that you can buy to do these kinds of things. Software is better, libraries are better. And there's a ton of actual real world applications you can use after you're done with FIRST. You can go do robotics in college or find a career in robotics, and then even later down the road, you can use these things to apply to machine learning, which is all the rage right now. At least if you live in Silicon Valley, I'm not sure how many of you do. So basically when FIRST started doing vision, it was in 2005, and they released this little board that you could plug into your robot called the CMU cam. And it was this thing right here, and what it could do is you could say, I want to track this exact color. And it would talk to you over serial or something. It would say, okay, I see a couple blobs of that color here, here, and here. And then you would write some software on your PIC microcontroller, robot controller, to go do stuff with it. And the first year we ever had vision, there were these hard plastic targets on the game piece. And almost no one did vision successfully that year. I think one team picked up the target one time or something. It was a really hard task because the lighting was different in every event. The camera wasn't that great, so no one really did it. That was bad. The next year they thought vision was really cool, but they noticed teams had a ton of trouble with all the lighting conditions. So oh cool, what if we add this lit target to the back of to the top of the goal? Make it real easy to find the goal. And teams were really successful at this. They were able to find the goal, point their turret or their robot at it to this giant goal and shoot balls into it. Super successful. The next year, cool, well we had a lit target last year and that was great, so let's have a lit target this year and that'll also be great. So the lit target was still great, but the problem was the scoring mechanism that year was putting inner tubes on this thing that could move all around. So even though you could see where the thing was, you could drive to it, you had no idea where the actual peg was to score your tubes. So same mechanism, much harder to do, wasn't that great. So a couple years went by, and we moved off of the CMU cam and the backlit targets to something like what we have now, which is a retroreflective piece of tape and a light that you would put on your camera. So you bring your own light source. You point it at the tape, send stuff back at you. And this was really great in 2012 because you could point at the basketball hoop, shoot into it, make it. And then 2013, same thing, same target, but people didn't use vision, and you didn't really need to because the target was 5 feet wide. So if your driver couldn't line up and hit that, you probably needed a better driver. So the first question you have to ask yourself, looking through all the history of that and how things have evolved and how some years it was, the target was great, but the task was hard, or the target was great, but the task was easy, you kind of need to know when to use this. So the first thing is you need to make sure that you have a reliable target. If it's something that's moving around and there's a fixed light on top of it, just don't even bother. If you can use a simpler sensor, like an optical sensor or an encoder or something on the field to figure out how to do this as well, like you should never be using vision to like tell your arm where to go. That's not what you want to do. And if you can align your robot manually, so like last year people, I saw some, which was really cool by the way. I'm really excited that people did this, but there's like vision tracking algorithms that could track the autonomous yellow toads. But you could start your robot right on top of the yellow autonomous toad. Like I don't know what that was for. But if you could start your robot right on top of the game piece, you don't need to use vision. You could just use local sensors like encoders. And in teleop, you can point a light at something. All these things are great. So really the only time you want to use it is if you want to get like a quicker alignment to the goal. So some of the kind of common things you could do here are, you're in autonomous mode, you want to drive over something like say a metal barrier, and then you want to point at a target. And then your robot goes into teleop mode, and what do you want to do? Well, you want to drive over a metal barrier and point at the target. So it's kind of the same thing. You don't need to have a special autonomous use case and a special teleop use case. You should write your code such that it works for both. But how do you get there? So kind of the main part I want to talk about is this visual servoing use case, which is, you have your robot has a shooter at the front or a catapult at the front. You want to point at the goal, put the ball in. Very applicable to what's going on downstairs over the next couple of days. So kind of the three main parts that go into doing this task are, you need to have some kind of camera on your robot and some kind of hardware to process the frames that come off of it. You need to have some part of software that detects the target, and then you need to be able to have a control loop on your robot that can actually do something with that information. So the first part I'll talk about is the camera. So kind of this is what most first teams use when they set up this kind of system. You have some people will put an IP camera on their robot and send video stream to their driver station computer over the Wi-Fi, and then you can write an application on your computer that does the processing and then sends it back to the robot. And that works really well. You can see what's going on the screen. That's really, really nice. The problem is that it might take 50 milliseconds for the frame to get to the laptop and another 50 milliseconds or 100 milliseconds for the information to get back. So you've introduced this artificial lag into your system. We can do better. So some teams may use what I call onboard mechanism, where you take a USB camera and you can plug it right into your Roborio. And this is pretty easy because there's a bunch of libraries that help you do this, and it's just a USB camera, so there's no extra wiring or power you need to worry about. It just boots up when your robot boots up, and all of that is great. But the problem is that the Roborio, or the Roborio as I like to call it, is really slow. It's not a very fast processor, so while you're doing all your other robot stuff, your vision's slowing you down. And then we have this category of kind of external processors. So this is some kind of off-board computer with a camera. There's a bunch of different ways you could do this. You could use this thing called the Kangaroo PC, which is like a battery-powered PC, the NVIDIA Jetson board, an Android tablet. There's a bunch of different ways to do this. And you can get it really, really fast and with a varying level of hassle, depending on what you use. It's more wiring, it's more networking code, all that. So kind of quickly recap that. There's a bunch of solutions, and not any one of them is the absolute correct solution. Some of these things are a little harder. This projector kind of cut off the bottom axis, but basically this graph, the bottom axis is like how hard is it to do, and on the left is like how fast is it to process. So something like the Pixie cam, which is the newest iteration of the CMU cam, is really easy. You can be like, track this color, and it will tell you that it tracked the color, and it works pretty well. But if you want to ask for the skew of the target, say you're shooting basketballs and you want it to align a little to the right, if you were skewed to the right so you could bank it off the backboard, can't do that. So, some stuff is slower, some stuff is faster. It's really going to be up to you to decide what you think is the best thing. So after you decide what kind of camera and processing hardware you want, you need to learn how to do target detection. So what I really advise here is use a library. There's a lot of libraries out there like OpenCV, Anivision. There's a tool you may have used called Grip, which is like a visual wrapper on
OpenCV. And all these tools are going to help you build your vision pipeline really quickly. Instead of, don't go in there and try to write code that iterates over every pixel and figures something out. It's just, don't do work that's already been done. So the basic thing, what you do is once you've decided what library you want to use, and once you've figured out how to get the image off of your camera, the way you actually do this thing for this year's target is the first thing I would do is do a color threshold. So you have this RGB image that shows you the target, and you basically want to take away everything that's not the target. And then you want to kind of group nearby stuff together and find different contours or blobs. And then you can look at the shape and size and all that of those and filter them out. And then you just find where the pixels are. And it seems really easy because it is. You could do this in like 5 lines of code. You just need to know what those 5 lines are. So I mentioned quickly on the slide before that you want to use HSV color thresholding, and the reason for this is really simple. When you get a frame off the camera, it's going to be an RGB format, and that's basically every pixel has a color value that is some % blue, some % red, and some % green. And that's really great because TVs work like that and stuff. But when you're trying to find colors in an image, it makes it a lot harder. For example, if you wanted to find green or bright green versus blue or bright blue, they kind of end up in the same area, so it's hard to tell one from the other. But on the HSV side, where H stands for hue, or like what color it is, S stands for how much color is like in that color. The less S you have, the more white you have. And the value is how bright it is. The difference between bright green and bright blue is actually a lot. It's much easier to find that difference. So definitely do it that way. So when you're getting your image, a few really easy things to do to make this easier is like turn off all the auto settings on your camera. So no auto exposure, no auto brightness, no white balance. Some cameras it's easy to do, some cameras it's harder. It really depends on what you use. And you want to turn your exposure time to be like the minimum your camera supports. So you basically want to have a completely black image other than the goal. It's going to make everything a lot easier. The more noise you have in the image, the harder it is going to do this thing, right? Like garbage in, garbage out. Yeah. So basically, like the most important thing you get out of this is, as I said, make the image as dark as possible. And if you can use some kind of live feedback tool to tune your HSV, that's going to make it a lot easier for you.
Yeah, and I'm just going to spend a couple minutes diving into how I found a method for doing HSV tuning that I found to be pretty robust over the years. So the method I'm about to describe, 2012, 2013, and 2016, the teams I've been on have used this method, and we've never had to go out on the field and calibrate our camera, because at the end of the day, you want your system to be measuring only the light that you're providing, which should be the same whether you're at home or here, from your little LED ring. So before I jump in, this is what we're trying to get to, right? So the before image, and it looks a little bit different. It's actually not too bad, but you can see this is actually an RGB image captured from the camera on 254's robot this year. And I believe it was captured, it may have even been daytime in our outdoor field. The takeaway here is this is a pretty dark image, and there's normal lighting level in this room. So we used a 1 millisecond exposure time on this, which means that the aperture of the camera is only open for 1 millisecond. While it's open, the light's pouring in through the lens, it's hitting the CMOS array at the back of the camera, and basically that's what creates the pixels that we see in this image. And you can see in 1 millisecond, not very much light got in, except for the light that was being reflected off this retroreflective target, because retroreflectors have this nice property that they return light back directly in the direction it came from, which when you have a coaxial LED ring, that's going to be right back at your camera. So you see the before image, see the after image when you do some HSV thresholding. You can't actually see it on the projector, but there is a very faint other goal there. So you end up with this black and white image, and once you have that, the rest of it, this process is pretty easy, right? It's a matter of fitting a contour or a blob to the big gold-shaped thing, and then determining whether or not it's what you're looking for. So how do we tune our HSV threshold to be like this? The first thing is watch out for overexposure. So this is an example. The left, again, is the image from our robot. The right is actually an image that's in the WPI-Live documentation for setting up the camera. And I'm not picking on them, but this was the first thing I could find that had a good example of this artifact. So you can see on the right, it's still a really dark image, right? The exposure time is still turned down pretty low. But something interesting happens here. Look at the color of the goal that's circled in red. If you actually look at the colors of those pixels, they're actually a little bit more like cyan-like. They're a little bit closer to white, a little bit more blue. And this is basically the same light source being used in both these images, but the color is very different. And what you're gonna find is the color on the left is much more green and less white than the color on the right. So what's going on here? So in order to answer that question, we have to understand a little bit about how digital cameras work. So like I said, when the aperture of the camera opens, light starts pouring through an opening in the camera, through your lens, and it's hitting basically a plane of these CMOS subpixels. These subpixels are basically like, you can imagine them as buckets that get full of photons, and then they output a charge proportional to how full that bucket is of photons. So you might have subpixels that detect red, green, and blue light. So the red ones only react to red wavelengths coming in, and blue and green, the same thing. And each of these subpixels can only measure so little or so much light. The bucket's only so big, right? So there's nothing blacker than black. And once that bucket is full, any additional light that you receive after you've saturated that subpixel, you can't do anything with it. You can't measure it. And why this is important is no LED ring you're going to buy is going to be exactly like green. If you know about like the RGB spectrum, it's a continuous spectrum. And LED rings are mostly green light, but there's blue components, there's red components, and overexposure actually can make the color of your LED light appear a little bit different to your algorithm. So here's a concrete example. Let me walk through this. On the left, let's say that these are the components of the actual light coming out of the LED. So it's mostly green, like 99% green, 25% blue because it's maybe a little bit of a bluish green, tiny little bits of red because that the frequency response of the LED isn't perfectly impulse-like. And on a camera that overexposes, we can see we open the aperture, light starts pouring in, and we very quickly reach this point where all those buckets are full on the blue and the green subpixels. So even though there's a lot more green light coming in, we can't really see it. So as a result, what we see in our image is actually bluer than what we thought we would get. So this becomes a big problem when you're trying to tune, because this specific effect is now more susceptible to other light sources in the room because that might tweak the relative ratio of blue and green. It's more susceptible to the angle of the target. It's actually going to change from green to blue to green again. And you can see if you have a properly exposed camera, maybe you actually, your image is really dark, but if you look at an HSV space, even though that green is very different looking than this green, the H component, the hue angle, is exactly the same between these two greens. So that's important versus, almost 43 degrees different for the cyan. So don't overexpose your image. And then you actually need to tune the HSV or HSL. It's a quick footnote, HSV and HSL are almost the same thing. Some tools and frameworks support one and not the other. Doesn't really matter. They're just slightly different formulations of the same idea. So if you want to tune an HSV thing to detect these goals, the problem is there's multiple ways that you can tune this thing such that it works great in your lab. There's many sort of local minima that you can fall into where it looks great in your lab, but then you're going to go on the FRC field, there's going to be some sign off on the side of the stadium, and you're going to see that. So what we want to do is find a superior solution, one that's robust. And it turns out, as long as you're not overexposing, hue becomes the most dominant component of this. So what you want to do is make sure you tune on hue first. Let the saturation and value be really, really high, accept almost everything. Let all that pass your thresholding filter. But you want to set your hue threshold as narrowly as possible. And I'm not going to walk through all of this, but there is some intuition, like hue values actually mean something. There's a universal standard for green is at 120 degrees. OpenCV uses a weird format that you can read about there. But so what this means is your threshold should, on the hue side of things, should make intuitive sense. Because many times in the practice field, I've gone and helped the team with their vision code, and I look at their HSV thresholding stuff, and they're doing a lot of stuff on saturation value, but their hue range is huge, and so this isn't going to be a robust solution for you. So once you've tuned hue to be as tight as you can, you want to basically make that as narrow as possible before you start losing pixels off the target. then you can move on to saturation and value or lightness. Basically, you expect to see high saturation. Saturation is like the intensity of a color. Brightness is totally dependent on the strength of how many LEDs you have and all that, so you can tune that too. So that's my side note on HSV tuning. My experience has been this method works really well for first. Like I said, I've never tuned my vision stuff on a field during that calibration time. I do like to go out there and whip out the tape measure and measure things, but that's better use of that time. Yeah, back to Tom.
Cool. Yeah, so the idea with the next part is once you've done your HSV or HSL thresholding and you have, some blobs of positive and negative values, you want to be able to find those targets and identify what they are. This shot, just for reference, is a screenshot of our vision tracking application this year. We wrote a custom Android app that runs on a phone that's mounted on our robot. So, yeah. As you can see from the image before, we've rejected the little blob of green on the left, and we've accepted the good blob of green on the right. So that's kind of what you want to do. So you can do this in a number of ways, but kind of some of the things that we've used successfully are looking at the blob or the contour size. So the contour is the image around your group of pixels. You can use like a convex hole function to find that. The blob is just the blob. You can look at the aspect ratio of it. So if you expect like a long, thin, long short target, like you should probably have a long short target instead of a narrow tall one. Make sure that you have 4 corners if it's a 4-cornered target. So if you have like that original one where it was kind of like cut off and you had a triangle, like that's no good. Same thing, vertical and horizontal lines. And fullness, which is kind of a neat idea, is if you take the outside of the target. So for example, in the kind of U-shaped one we have this year, the bounding box on that looks like a rectangle, but the amount of area that passed the threshold inside of it should be a U. It actually turns out it's around 35% of that blob should be filled in. So you can threshold on that as well. You could say, if the amount of area inside of this is greater than 40%, like this is probably a sign or something like that. This stuff is stuff you want to play with. It's a little more hand wavy, but you can do that. You can do this using some of the graphic tools that we suggested earlier. So once you've run, I know we ran through that really fast, the whole vision part of it, but it kind of is only half of the battle, right? You need to be able to find the targets really, really well, but you also need to make your robot do something with it really, really well, because this is not the first vision tracking competition, this is the first robotics competition. There's more that goes into it than that. So I'll go through a couple of like pretty simple examples to show you how to get your robot to do something with it. So this is the control loop part of the initial block. So you can go and you can figure out where the target is, and you can figure out like, okay, well I found the target and my thing is 320 pixels wide and it's the 120th pixel, so like if it's to the left of the middle, I'll like turn left, and if it's to the right of the middle, I'll turn right, and I'll just keep doing that. And that would be bang bang control. And I think you'll find that this does not work anywhere close to what you think it will do. You're just gonna probably turn left forever. So okay, the bang bang wasn't too good. I applied too much power, I overshot. Maybe I could do PID. I learned about PID before, it sounds cool. I'll like calculate the error and then drive in nicely. I think you'll find that this doesn't do what you want it to do either. And the reason why is because of the frame rate. Most likely you're gonna be using something in the like 20 frame per second range, which is just not really fast enough to close the loops of your drive control on. And also if you just do this, that camera image is not linear across. If your field of view is 60 degrees, 5 pixels from the center is not going to be a linear correlation to 5 pixels from the edge. It's going to be much farther. We'll talk about that a little more later. So all of these pieces of control code that rely on a linear output aren't going to have that linear input. It's not going to work. So what can we do better than that? So what we really need to do here is take what we think we see and turn it in from camera units into real world units.
So you need to be able to take that pixel value and turn it into a real world angle or distance and use a different controller to achieve your goal. So maybe you want to turn towards the goal, you calculate that you're 15 degrees away from the goal, you should write a gyro control loop that can take that 15 degrees and then use the gyro to turn. Because the gyros are really fast, so you can run that control loop at 100, 200 hertz. It's way faster. So definitely convert your units and use a secondary sensor. It's going to be much better. And what will this do for you? So it's good because your robot control is not limited by how many frames you can process. You can actually have a really slow vision processing algorithm. This will work fine. You can process 1 frame per second. It doesn't matter. You're going to get the frame. You're going to move, and you're going to be done. The problem with this is that you need to convert units into reference frames. I'm not sure. Maybe you're not sure how to do that. We'll talk about that a little bit later. And if you have a really slow robot, this might actually work. This approach might work really well of just bolting on another controller. The problem is that latency in the image and the image processing will still be kind of a problem. And I'll show you why here. So in this example, R2-D2 is trying to find the serious vision tracking target so he can shoot his boulder into it. So he, in the first part, sees that he's theta A away from the target. So he's like, beep boop, I'm gonna turn to theta A. So he drops that into his controller. He starts spinning. While he's spinning at t=1, he captures another frame. So he's spinning right now. He's at a different angle, he captures another frame. He's still spinning because he's using a gyro control loop. And he gets over here, at t=2, that's when that frame is done processing. So he's getting the result from this frame over here. But he's moved since then. So now he's like, all right, well, I'll just dump this error, theta b, into my controller. But the difference between where he is now and where he was before is actually over there. So he's gonna shoot past and then go back, and it's not gonna be great. You're putting an artificial delay into your system. And as I said before, if your robot is sufficiently slow, this would probably work great. But if you wanna do it, if you wanna have a really snappy turret, or you wanna drive really fast across the field and track the goal at the same time, this is just not gonna work. So what you really need to do is use the information you have about the frame and the information you have about your robot's position on the field, put those things together and account for latency that way. So what you really need to do is keep a history of where your robot's been. So this has become a little more complex now. Now you need to look up where the camera was when you took the frame. You need to do your conversion, and then you need to adjust your output based on where you are now versus where you were when you took the picture. So this is a really simple kind of overview of how to do this. So what you want to do is you definitely, every time you take a picture, record the time. This could be system time, this could be whatever you want. You just need to have some idea of what time it is now versus what time it will be later when you're done processing it. And you also, in the same time reference, want to keep a history of your robot pose. So if this is just all you want to do is point your drivetrain at the target, all you care about is gyro angle. If you have a turret, you maybe care about turret angle. So you need to keep track of those things. So basically what you can say is, when you're done capturing your frame, at time t, when the frame was captured, you can go and look up, my robot was at position P. And knowing those two things, and knowing the result that your image processing gave you about the error that you currently have, you can mold those two together and come up with a more accurate representation of where your error should be. So there's this is just pseudocode, but it kind of gets the idea across. And the requirements here are that you need to know the pose history, which there's a couple ways to do, and you need to know the image timestamp, which there's a bunch of ways to do as well. We can talk about that later. But the great part about this is you're going to have smooth, really, really precise control. Your robot's always going to be pointed in the right place, which is what you want. So on the last couple of slides, we had a couple of these really confused-looking faces. So now we'll go through 3 steps that tell you how to take those confused faces and turn them into things you understand.
Yep, we're going to turn you all into green check marks. So yeah, Tom just walked through, sort of 3 different tiers of control. And to be clear, like depending on what you want to do, any one of those might work for the requirements of your given application. Using pixels for PID, converting the pixel error into a real-world unit, and compensating latency. These are just additional things you can layer on top for better performance. So the first thing that you need to do, though, if you want to take that first step from pixel-based PID to the pose-based visual servoing where you use a gyro or encoders, is you need to do this reference frame conversion. So I might see that the goal is 30 pixels to the left of the center of my image. How do I tell my gyro to turn 30 pixels? So there's a simple and almost right answer to this, and then a little bit more complicated actual right answer to this. So let's walk through an example. And this is the way that most teams have done this in the past, and that's okay. It's approximately accurate and probably good enough, especially if you have a narrow field of view camera. So let's say we have a camera with a horizontal field of view of 60 degrees. The image is 640 pixels wide by 40 tall. We detect a target in the image at some coordinates. I said 45, 250. So what we can do is we can say it's 60 degrees across. It's also 640 pixels across. Divide the two. I get a little under 0.1 degrees per pixel. So I can count the number of pixels over from the center. Side note, the center of an image in most computer science context is actually going to be a fractional pixel because there's an even number of pixels across here. We start at 0. So it's actually between the 319th and 328th pixel is the center of the image. So I can get the offset of the target from the center of the image, multiply it by that unit conversion, and then I'll get an answer. So in this case, it's negative 25.6 degrees. And that makes sense. And like I said, it's a pretty accurate approximation. That is a linear approximation. It assumes that 1 pixel is the same angular measurement all the way across your image. The problem is, as the field of view of your camera gets larger, like for example, a 90-degree field of view, you have this error. So like when by the time you're halfway between the edge of the image and the center, there's actually a few degrees of error between where that angle truly is and where you would have estimated it at. And this is not because the lenses are imperfect or anything. This is just a fundamental issue with doing the conversion like this, because our imaging plane is flat and it's not curved. And I'll show you this. This requires a little bit of trig. So if you understand trig, hopefully you'll be able to follow along. So I'm going to introduce a concept called the pinhole camera model. And maybe in a physics class or something, you've actually made a pinhole camera. It's kind of cool. Pinhole camera is basically like a cardboard box with a tiny little hole, an infinitely small hole in theory, but a tiny little hole, and light passes through that hole, and then it hits the other side of the box. So you see like you have an apple out here, the rays of light all pass through here, they hit this plane on the back, we can call it the image plane, that's where the CMOS sensors in your digital camera all live. And yeah, so each pixel gets the light at that angle, and one thing you'll notice is this image is actually upside down and flipped left to right. That's true in your cameras too, but most cameras will then flip it for you. And even though our cameras are not pinhole cameras generally, there's lenses, there's complicated things going on, this model works pretty well. And this model has a parameter called focal length, or F, that's very, very important. And focal length has a lot to do with our field of view of the camera. So I'm going to switch to this other diagram, and let me just explain this, because I'm going to use this for a couple slides. This is the top of your pinhole camera, right? So we're looking top down at a camera. This red dot is that little tiny hole where the light can pass through. This is the image plane in here. So the image plane has some width, because remember we're top down, so this is a width. And then we have this focal length, the distance from the pinhole to the imaging plane. And then there's this imaginary concept called the optical axis that goes from the middle of the image plane out through the focal point. So what's the field of view of a camera? There's actually an equation for this, which is kind of cool. This is totally trigonometry using an arctangent. So what we can notice is the ratio of my focal length to the width of my image plane has a relationship with my field of view of my camera, because we have a triangle, right? So this is one side of the triangle is half the width, one side of the triangle is the focal length, and then the angle that the hypotenuse makes with this line is half the field of view. So, assuming my math is right, that's the equation you get relating image width, focal length, and field of view, and another formulation. So, basically, if you know 2 of those things, you can find the third. And for just about any camera you buy, you're probably going to know two of these things. You're going to know your image width for sure, because we can measure that in pixels, and even though I know we're trying to convert from pixels to a real world unit, in the math we're going to do right now, that unit's going to cancel, so it doesn't really matter. And you can probably also estimate the field of view of your camera, because it probably tells you somewhere. Or you can actually do an experiment to measure it, and that's called camera calibration. But anyway, what we want to do is find this focal length parameter, because that's going to be what really lets us do the proper conversion between pixels and angle. I'm going to move through some of these slides quickly because it's hard to dive through this material like this. So I'm going to take some of these equations at face value, and then when the slides are made available, you guys can work through them and feel free to ask questions. But basically, with the focal length, we have the equation of a line here. So the x-axis of the line is f. The slope of the line, if we have a point out in the world here at some position x, y, and z, the slope of this line is x over z. And there's an offset from the edge of the image of cx. This is y equals mx plus b, the equation of a line. So for each point in the world, we can use this equation and find the pixel coordinates u and v. U and v are commonly chosen for the x and y coordinate in an image to disambiguate it from the xy coordinate of whatever you're looking at. So we have this equation that for any real world point, we can figure out what pixels we expect to see that point at in our image. Cx and cy in this case are the center pixels, which are usually like half your image width, adjusted by 0.5 for the reason I talked about earlier. So that's great and all, but what we really want is to do the reverse. We know which pixel we see our object in, but we want to know where in the real world is that object. So what we have to do is invert this equation. So we can rearrange, do some algebra, but we're going to have a problem here, right? Because there's this z. The z is how far away is the object. We can't solve for x because it depends on z, but we can solve for x over z. And same thing for y, if you imagine a side view of that pinhole camera. And it turns out, for now, it doesn't actually matter that we don't know the range, because it's going to cancel out. But the point here is that for any point in the world, we know what pixel it's going to hit. But we cannot invert this equation just on its own without other information, because if we know what point on the pixel, what pixel a point in the world corresponds to, it actually could be any of these points, right? This is a line that we're seeing. It's not actually a point in space. And this is a powerful idea. That said, what we're trying to do right now is just find the angle of the target. So we can find the arctangent of x over z, and that's equal to the arctangent of this distance over this distance. So it's similar triangles. This triangle and this triangle are exactly the same. And it turns out if you run through for all the pixels in your image, you end up with a plot like the red one here. So not quite a straight line, it's not quite linear. The pixels at the outside of your image are, actually measuring a little bit more angle than the ones in the inside. But again, if you want to use the simpler approximation, especially with a fisheye or wide field of view lens, it's probably going to work okay. It does have this really nice property that at the center of the image, it gives you the same answer. So as long as you keep running your control loop and moving a little bit closer every time, you're still going to end up in the same place. But the pinhole camera model we'll come back to in a second, because once we want to find the distance to our object, then you really got to know what you're doing. So again, looking at that same concrete example, so we have the same camera with the 60-degree horizontal field of view, same size of the image. If you plug into those focal length equations a few slides back, you end up with 554.3 pixels as your focal length. You can then plug that into our yaw angle to target equation, where you take the pixel, 45, minus the center of the image at 319.5, divide by the focal length, take the arctan, and you get 26.3 degrees, which is, in this case, for this camera, this is like 0.6 degrees difference. Is that a big deal? If you're an outer work shooter this year, that actually could be the difference between making a goal or not. That said, it's totally up to you guys in your application whether it's worth doing this math, but I happen to think it's pretty cool. And now, FYI, so in the real world, if you're doing robotics in academics or in industry, you want to get as precise as you can. And you actually go a step further. We don't trust manufacturers when they say this is a 60-degree lens, because manufacturing tolerances and other things, it's seldom exactly what they say it is. So there's actually processes you can do where you capture a bunch of images and then run some sort of optimization technique, and you can solve mathematically to figure out what the focal length of your camera is, and even is the center pixel of your image not actually the center pixel? There's kind of a strange idea, like the lens is misaligned. distortion parameters. So this camera calibration is a big deal. It's in college vision courses, this is one of the first things that you would learn about. So that is how to convert pixels to angles. Switching gears just a little bit, latency compensation is the second enabling idea if you want to get past this, inevitable behavior that if any of you guys have actually tried to implement this, you've probably seen where you see the target, you start moving, you see it again, but by the time you've reacted, you're now someplace else. So the first question is, do you need it? It totally depends how quick you want to be. And the good news is there's a couple of quick hacks you can use that are pretty easy to implement that will go a long way. And then there's a little bit more complicated solution that does this about as well as you possibly can. So the quick hacks are, make sure your control loops are overdamped. What does this mean? Overdamped means basically sluggish. They don't overshoot, they're slow to react to things. So basically you're compensating for the fact that your measurement is in the past by your controller being pretty slow to follow that, and you'll converge to the target eventually. Comparatively, you can also think about doing this. If you think that you need to turn 20 degrees to the left to see the target, well, maybe divide that in half, only move 10 degrees, and you keep doing that. And this will prevent you from overshooting because you're basically putting a low-pass filter on your measurement. This is obviously not an ideal solution because you're inherently moving faster and less precisely, but it works, especially if you just really want to get rid of this oscillation. And another thing I didn't write here, but definitely worth thinking about, a lot of times, as long as you're well calibrated, you understand how your camera relates to your robot, maybe one frame is all you actually need. You can just stop your robot, take a frame, be really confident you know what that angle is, and then turn without having to worry about synchronizing things once you're moving. Or maybe you turn and stop, take another frame, and then do a couple iterations of that. Because that totally sidesteps this problem. But in the spirit of the talk and the spirit of our team trying to push the boundaries here, I'm going to talk about some of the work we did to do latency compensation to let our robot track the goal while driving full speed around the field this year. So, exaggerated example of what we're trying to do. Let's say you have a blue 8-wheel drive turreted robot. You detect a goal. The robot pose at the image capture time is here. The robot pose now is here. Clearly, if you didn't do any latency compensation, we're going to say, well, that's the angle of the turret to the goal. So we're going to end up, by the time we're over to here, we're going to be pointing over there. Not ideal. That's what we actually want to do. So, what do we need to do here? We need to keep track of the robot pose over time. The word pose, we've used this a couple times. I want to take a quick moment to define it. It turns out, pose in this case means a few different things depending on what you're actually trying to do. If you're trying to rotate in place, maybe pose just means the angle of your robot. If you're trying to turn a turret, maybe it's just the angle of your turret. If you're actually moving while you do all this, maybe pose consists of both a translation and a rotation. It's like maybe you're integrating encoders over time, like you can do in autonomous mode, where very quickly you check your encoder counts and increment your position in the field. And that's actually the version of pose that we're referring to on the 254 robot this year. And if you're integrating pose over time, let's say 100 times a second, you read your encoders and you update where you think you are on the field, that also means you can just hold on to that information as you calculate it. So let's say every 10 milliseconds you remember where your robot was. This would be really helpful if you knew that there's latency and you're crossing your camera frame, but you could measure accurately when that frame was taken. Then you can go back in time and look up, this is where I was when this was taken. This is where I am now. So I can do the calculation, and then I can adjust everything to take into account how I've moved since then. So, I think this looks a little bit something like this. So let's put some words on things, and cut off at the bottom, but you can probably imagine what goes there. So robot pose now. There's an X at capture time, Y at capture time, and theta at capture time of the robot. Detected goal. There's an X, Y, and theta there. The robot pose now. There's an X, Y, and theta there. So these 3 different components. What I can do is compute the goal pose based on where I was then. So if I see that the goal is 100 inches in front of me and 5 degrees to the left, I can do a vector addition and add 100 degrees, or 100 inches and 5 degrees to my prior pose, figure out the actual location of the goal, and then from where I am now, I can just compute the angle using the arctangent, the range using the square root of the squares of the differences in x and y. This is the hypotenuse of an equation, the Pythagorean theorem. But wait a minute. So up until now, all we know is that x over z and y over z. We know these rays along which the goal is. But if you want to do this latency compensation the way that I just described, you actually need to know where that goal is in all 3 dimensions. This doesn't apply if you're just rotating in place with the camera relatively centered, but if you're not doing that, then you absolutely need to know distance. And besides which, you might want to know the distance to target for other reasons, like telling your shooter how fast it needs to spin or a launch angle or something. So let's talk about, I think the last major topic is finding the range to a target. The camera gives us angles to the target, like I talked about before. And then we can think about these as a line or a ray, more precisely in 3D space. So the origin of the ray is the camera lens, and it shoots out through space forever, and somewhere along that ray is the goal. So how can we find a specific point on this line, on this ray? What ideas do we have? Well, what happens if we intersect a line with a plane, right? Assuming that they're not parallel, which is probably not the case, because if that was true this year, your robot is too tall. But if you know that the center of the vision target is, say, 89 inches off the floor, you have this plane in 3D space, 89 inches off the floor. You know what height the camera is on your robot, presumably, or you can measure it. Same thing for angle, and you can compensate for that and shoot this ray out of the camera and find that point where they intersect. That's one way to measure range, and it turns out that works pretty well. That's what we've done in the past and this year. There's other ways you can use this too. You can use a secondary sensor like a LiDAR. So you can imagine you have the LiDAR light, single beam laser radar, coaxial with your camera, and it shoots out and you get a return off the target. The problem with this is actually the center of the vision target this year is air, right? There's a vision target around the opening of the goal. So you have to make sure that this only really works in certain situations. You can use a second camera, in which case you actually have a line and then another line, and you find the intersection there. That's really tricky because those lines might not actually intersect, so you have to find like an approximate intersection. And lastly, you could use target size, right? So when something's close, it's more pixels. When it's further away, it's fewer. That one, I've not seen that work very well. It does not have very nice noise properties. As you jiggle around or change the angle of the target, the size can actually change quite a bit, especially by the time something's far away. There is not very many pixel difference between something that's like 100 feet away versus 150 feet away. I generally recommend one of the other approaches. All right, so related to this, most of the time your camera is not at the exact center of your robot for practical reasons. So you're gonna have to compensate for how the camera's mounted. And I'm not gonna walk through this topic very much here, other than to point you, we're gonna release our code at the end of the year. And that contains some math libraries that actually help with this a lot. And I think FIRST really needs something like this to be available. Coordinate frame conversion is that's what, as a roboticist, I do a lot of at work, right? So you have sensors and grippers and wheels and the center of your robot and your objects in the environment. And each one of these things you can think of as a coordinate frame. Like they're at the origin of some like X, Y, Z thing. And how do these things relate? And how do I know, if the camera sees the goal somewhere, well, where's that goal relative to the base of my robot? And there's math libraries you can use to do basically 2D or 3D kinematics and convert between all these things. And again, the math here is not super tricky, but it would take another hour to go through. So again, I'm going to refer you guys to the forthcoming code release. Okay, so we just blew through a lot of material. And at a lot of depth too. So I would be shocked if anybody actually absorbed all of that, and I know there's gonna be questions. So we're gonna get to those in a sec. I just wanna real quick run through some of the top takeaways and best bets here. One, do you really need vision? There's different philosophies on different FIRST teams, and I think this is a great thing. There's a lot of diversity in the program. But if your goal is to be as competitive as possible in a given year, there are years where vision is just not the right answer. That doesn't mean that you can't do vision. Vision is awesome, it's cool, it's a great learning and inspiration experience, but sometimes it doesn't map really well to the competitive aspect of the game. So think about that. Know your resources. It's hard to do this without having someone on your team with a little bit of experience, at least in computer science. A little bit of vision experience is better. But don't design your robot around this like auto tracking turret thing if your team has never done anything like that. There's a steep learning curve. And I think it's an admirable aspiration to do that, but it's never a good experience when you just are totally unrealistic. Know the hardware trade-offs. So picking the right hardware makes your life a lot easier or a lot harder. And a lot of hardware, I think it is. So, weigh the pros and cons of each of the solutions we talked about, and yeah. LED ring lights, good camera settings, proper HSV tuning. That's been a great recipe for the past few years, assuming nothing else changes. I think this is going to be a good way to go in the future. This can work really, really well. Centering the camera on your robot or mechanism has some simplicity advantages. You might not have to worry about like all these offsets and coordinate frame type things. Then again, sometimes you just can't realistically put the camera in the center of your robot. Doing PID on pixels does not work super well. Encoders and gyros are awesome. If you want to tune a control loop for vision, don't try to just hook up a camera to an untuned PID loop and expect it to work great the first time. You got to make sure that you can actually turn your robot to the angle you tell it to. And until you are able to do that, you shouldn't think about adding vision. And then lastly, a tip. This is just a random thought that didn't fit anywhere else. Tracking or filtering multiple observations over time. So, when you're looking at a goal, keep track of where you saw it now, where you saw it like over the last 5 frames. A lot of times, even if you have a low resolution camera that vibrates around a lot, like I know on our robot, our camera is vibrating all the time. It's actually amazing how much it vibrates. You can average those together, and for free, you get back a lot of accuracy improvements. So, questions?
Back there.
Does it matter what color your LED ring lights are? So yes and no. Yes in that you want to make sure that you don't choose a color that's already heavily present on the field. Years where there's field lighting that's red or blue, you might not want to use those because they might be able to put out enough photons to confuse you. You don't want to use white light because it's hard to do hue thresholding on white. There's a slight technical advantage for green, but it's very, very slight. It gets into the fact that most cameras have about twice as many green subpixels than red and blue, so you have a little bit more precision there, but that's lost in the noise, to be honest. So not a huge difference. I've used green most years I've done this simply because there haven't been any other green light sources in the field.
Yeah, we used blue in 2012 on 254 because our lead mechanical mentor thought green looked ugly, so, and that seemed to work okay.
Yeah.
So when using OpenCV's like Intel libraries, does it really matter if it's Python, Java, or C?
Oh, that's a good question. So when using OpenCV's libraries, does it matter whether using Python, Java, or C? It turns out the answer is not really, because most of the high performance stuff that's churning through, iterating on those pixels, that's all using a C library, or a C++ library actually. It's either JNI'd or swig wrapped for Python. So there's convenient APIs for OpenCV, but you don't actually lose that much performance overhead for doing that. Yeah.
How does the arrangement of the lights affect performance?
How does the arrangement of the lights?
Yeah, is it like in a ring or some other configuration?
Oh, so yeah. So what's important here is with a retroreflector, it's going to send that light back in the exact same direction it came from. So you want your light source to be as close as possible to your camera lens. So rings are nice because you can concentrate a lot of LEDs, all very, very close to your camera. It doesn't have to be. You could put discrete LEDs or a couple of bars of lights, but rings are a nice way to get as many light emitters in as close proximity to your camera lens as possible.
I have 2 hopefully quick questions. What kind of camera do you guys use on your robot, and how do you communicate between your off-board device and your robot?
Yeah, so on our robot, I'll give you a little more than that. So we originally wanted to use the NVIDIA Jetson board with a USB webcam to do this. Probably some people in this room have used that solution. And we found that we couldn't get the board to boot reliably when we were driving over defenses. So we wanted to have something that had its own battery in it, so we moved to an Android phone. So we have a Nexus 5 on our robot, so it just, whatever the camera in a Nexus 5 is. And the way we talk to our robot is originally we were going to use Ethernet cable from the Jetson and talk over UDP or TCP. But now the Android phone has this really cool thing where you can use, and Team Spectrum did some work on getting this to work, so they should get some credit. You can plug your Android phone in with a USB cable and use ADB, which is the Android debugging bridge, to set up a port forward between a port on the phone and a port on your computer, which in this case is the robot. And then you can just talk TCP over that. So you can talk TCP over a USB cable. So we just talk to it like another computer over a network. Yeah.
Yeah, the Android phone, so we have a lot of cleaning up to do with that, but I also want to release that code because, you know, it just kind of makes sense. You know, like Tom said, we tried some other things, but what's great about cell phones is they're pretty cheap. So an Android Nexus 5 you can get for like 160 bucks now on Amazon. They have really good cameras, like relatively speaking. For this application, they're awesome. They have a built-in processor and battery, which is great because, and it's legal because it's COTS, built-in COTS battery. And the processors are being designed more and more to do image processing type things because people want to, you know, do games and Snapchat filters, like all those things, like that's image processing. And the hardware on board a phone is like, you're hard pressed to find actually a better, a more elegant solution than that. And on top of that, you know, camera makers want people to write apps using their devices, so there's pretty good documentation, pretty good APIs for using the camera. For example, the Android camera, we can get a timestamp when the image is captured, which is awesome. That's hard to get with a USB camera. We can also, you know, ask it, each camera is like factory calibrated, so we can ask it like, what's your focal length, and it will just tell you. So stuff like that is really, really nice. Plus you have a screen and a touch device, so you can, you know, just go and tweak stuff on the field. Like we have sliders that we can use to adjust our filtering if we ever needed to, which we haven't used, but it's fun to demo.
What language was used for that, for the phone?
Yeah, so Android's main language is Java. We actually set it up where there's a JNI part, so basically there's a lot of boilerplate you have to use to get to the point that you can use OpenCV, but once you have your image, you can actually use either Java or C++. So we actually did all our vision stuff in C++. Yeah.
One of you, no, back, yeah. Yes.
Oh, I was wondering how useful is like steganography, like using two cameras at once to find like a point in 3D space.
Yeah, so that can be useful if you have no other constraints that you can use, right? So the question was, you know, how useful is it? It's like stereo vision, basically, using multiple cameras. And then you can, you know, see the correspondence between those two things. That's doing that, basically, it's trying to intersect two lines is what you're trying to do there, but really. That works okay, but usually on the first game field, there's other like constraints that we can use that are better. Like the fact that something's at a known height, that's a really strong cue that you don't want to like get away from. That said, I know other teams like 971 use the stereo system this year. It works. It's a lot of work. In particular, synchronizing it so you get a left and a right image at the same time is a tricky problem. And in academia and in industry, we pay a lot of money for cameras that can be very precisely triggered, so you get two frames at the same exact time. And that's really hard to do on a FRC budget. So great fun.
When and where will these slides be available?
I'll definitely post a link to the Chief Delphi thread about this, and we'll put it on team254.com. And the code releases, usually that'll be in the summer sometime once we have slept and can go through the fine-tooth comb and clean stuff up for you guys.
Back, 2848.
Does it matter what communication protocol you're using, like USB or?
Not really. One of the things you may want to do if you're talking over a protocol that may have some, or a link that may have some latency, is through the timestamp in your packet or in the message. So it's either like do a clock sync and say at this absolute time I took the frame, or if you have a more reliable link, which like on your robot will be an Ethernet cable, which is gonna be fine. You could just say I took the frame N milliseconds ago, and then when you get it on the robot, you can just account for that. Yes.
We've been working in LabVIEW, and I'd like to know if you know how accurate their vision is. Like they have a thing that just says find the goal, and it just uses their NI stuff, the eyes and whatever.
Yeah, unfortunately, I don't know a whole lot about that stuff. This is it's a double-edged sword in FRC, how many choices we now have with like languages and different ways to build a robot, because unfortunately there's very few people now that are experts in all the ways to do it. And when it comes to LabVIEW, I'm definitely not an expert. That said, I actually know there's another conference that's taking place at this event, which will be Greg McCaskill and Brad Miller talking a little bit about grip and the WPI and NI side of things. Maybe they'd be able to answer that question. I'm actually not sure whether it's already happened or will be happening, but tomorrow.
Tomorrow, you're
Yeah.
back. There you go.
Yeah.
Next to the door.
How do you deal with
We buy the Spartan board, and it doesn't drift.
Yeah. Well, the other thing though is too, like, you know, we drive over the fences and it's a 2.5 minute long match, and the gyro's gonna drift over that time, right? But it doesn't really matter, because usually we're using the gyro to turn this like relative angle. So it doesn't matter if the robot thinks it's at 0 or 180 degrees or 90 degrees. It'll just see the goal and know the relative angle there. And then locally, like over a second or two, gyros are awesome. You're hard pressed to do a lot better. Their big drawback is they drift over a long period of time, but you let it drift. It would only be an issue if you like wanted to see the goal, then close your eyes and drive around, come back, open your eyes and like point at the goal again. But that's not usually a scenario. Usually you can reinitialize by seeing the goal.
Yeah. Also, there's some tricks you can do to get your gyro drift down. You know, we do it in our code, but while you're sitting on the field waiting for the match to start, when your robot's disabled, you can constantly be re-zeroing your gyro. And as soon as the match starts, you throw away the last calibration value you're working on because you know that one's not right. And that helps with like almost all of these issues that people have. Right there.
How do you deal with false positives? Like when you see a target that's the right color but it's not the target?
Yeah, so the way we sort of do vision, it's sort of what we talk about. So the first thing we do is the color filtering, and then we do a whole bunch of different shape checks. So is it like roughly square? Is it the right aspect ratio? Is it the right fullness? And at each step of the process, we like walk through all these steps for each blob that pass our color test, and we just throw things out as they fail those tests. So by the end, I don't actually know that we've ever had a false positive. We have some false negatives, like where you don't see the target because the image got blurred or something, but that's not as big a deal. I think with a little bit of iteration, you can actually come up with something that's pretty darn good at not looking at things that aren't the goal. Funny story there, I do remember like in 2006, at the Philadelphia Regional, this is the year they used the lighted green thing. I had a big problem with this, because it worked great at our school's test lab, tracking the green, but there was this team there, maybe you know them, Team 365, they wear bright green shirts. And in autonomous mode, one match, the turret turned and we shot a guy in the stands. But the good news is with retroreflectors and bring your own LED, like modern vision, you can get pretty darn good.
At the table, while you're all doing this, but you.
Did you guys have any issues getting ADB running on the robo-reel? Like, I'm curious how you guys got that.
Yeah, we, as I said before, I forgot their team number, 3847 maybe, but Team Spectrum, they have a GitHub thing that we just stumbled across where they had cross-compiled ADB to work on the RoboRio's architecture. So we just stole that. That was it.
Yeah, it's still sort of a hacky solution. There's a better way to do this that involves becoming an Android accessory, but everyone can try to do that. But
So you guys are running like network tables or something similar for the
the robot has a TCP server, and the camera tries aggressively to connect to said TCP server, and then sends it basically a JSON blob every 50 milliseconds. Yep.
So my kids have this problem where they're trying to tune vision code and it's like cloudy out, and there's a lot of noise because light's being scattered everywhere. Like you won't cast a shadow, right? So it's really hard to get rid of that noise. Do you have any suggestions here?
yeah, so the question is tuning outdoors with clouds, and you end up with a lot of noise because no matter how many LEDs you bring, the sun will always be able to outshine you. Is sort of what it gets down to. You notice we have an outdoor practice facility too, and so whether we like it or not, our stuff has to be like all weather functioning. But so I think running through the steps and the HSV tuning part, I suspect that there's ways that you can make that not matter. So yes, it's noisy. Yes, there's lots of light there, but that light is not the same hue that you want to find. So I bet if you go back and revisit your HSV tuning and maybe also your camera exposure settings, you'll find a solution that works for that.
Yeah, smaller exposure and tighter H is always better. Any other questions?
How do you determine how much latency you have in your processing system?
Yeah, so for that, you can basically like record the timestamp the very first time you see a frame. Like as soon as you see that the packet has arrived or however much, you can record the timestamp there. record the timestamp when you're done processing the image. That gives you part of the equation. That's like how long your code takes to run. But I think what you're really asking is, like, how do I know the delay between when the image is actually taken and when my code sees it? And it depends on the hardware you have. Some hardware, like on the Android phone, you can get a timestamp. You can ask the phone when was this exposure actually started. For consumer webcams, you generally don't have that. So what you have to do is basically run an experiment to figure out what that value is. The good news is it's relatively constant. You can estimate it once and it'll be almost right most of the time. The best experiment I've seen for doing this involves basically you take a video of a screen where you're displaying the stream from the camera along with the clock. So you end up with this like mirror effect where you see the screen and then the screen and the screen and the screen and the screen, but there's a different time at each of those frames. So that's actually one way you can try to measure it. There's other ways too involving like you can light an LED controlled by a microprocessor and then record how the time that you lit the LED and the time that the first frame you get back sees that the LED is lit. That's another way to do it. In general though, for like a USB camera that's used primarily, like a Logitech webcam that's used for like teleconferencing, it can be on the order of 100 milliseconds. Like it is a pretty significant latency that's built into the camera. It's because they just haven't optimized for that. They'd rather encode it on board and if you're just video chatting, it's not a big deal. But if you're trying to do robot control, it is a big deal. To sum up, the answers are either find a solution that can give you a better timestamp, or you're gonna have to estimate it yourself. And either way can work.
Again, back.
What was the latency you guys experienced with the Nexus 5?
So I think the total time between when the image exposure started and when we're done processing it is on the order of 60 milliseconds.